I still think it'll be mostly dry around noon. We'll see about a 30% chance of storms this afternoon. High temperatures will push 90 degrees. It will be warm and humid today. Any storms that do pop up
in southern states such as Georgia, we struggle to dehumidify and cool our homes in the summer. HVAC systems account for 40 to 60% of total energy consumption in both residential and commercial buildings. Humidity itself drives energy consumption, as the more humid the air is, the more energy that is required to perform the cooling process. As the system cools water vapor, it condenses and becomes a waste product. Our planet faces both an energy and a water crisis. There is a growing imbalance between the world's increasing demand for energy and the limitations or consequences of current energy production methods. For a planet that is 71% covered in water, only about 1% is accessible freshwater for human use, and over 2 billion people lack access to safe drinking water. What if I told you there was a single solution that could aim to both reduce energy consumption and provide potable water as a byproduct? Our team, the Desiccats, has been working on this solution for the past 12 weeks. In collaboration with Georgia Tech's Energy Innovation Lab, our team has put together a prototype. This is the HYDRA, which stands for Hydroscopic Dehumidification and Recovery Applications. The HYDRA is a novel HVAC system adaptation that dehumidifies air prior to cooling, which decreases the overall energy consumption of the process. As seen in this chart, with higher temperatures and higher relative humidity percentages, the energy consumption needed to perform air conditioning increases. Heat exchangers coated in a salt hydrogel passively reduce the relative humidity of the air, eliminating condensation of water on the evaporator. This heat exchanger unit, once it has absorbed nearly 4 grams of water per 1 gram of its gel weight, can be used as the condenser unit itself. The hot coolant drives the desorption process, in which the gel will release potable water. Ideally at full scale, there will be 2 stacks of gel-coated heat exchangers. One will be acting to dehumidify the incoming air to the system, while another will be recharging as the hot coolant forces it to desorb its water. The gel central to this process is a material known as a hydrogel. Hydrogels are 3-dimensional, water-swollen polymer networks that can absorb and retain significant amounts of water. In this project, we use polyacrylamide, a synthetic polymer, to form the base of the hydrogel. Lithium chloride is then added to the polyacrylamide because it is a hygroscopic salt, meaning that it readily absorbs moisture from the air. It enhances the water absorption capacity of the polyacrylamide hydrogel itself. Together, they create a material with a high water uptake capacity that readily absorbs water from the atmosphere. By casting the gel around a heat exchanger, we are giving it a great surface area from which it can draw in water from the air. The hope is that by the time the air passes over a series of gel-coated heat exchangers and reaches the rest of the HVAC unit, its relative humidity is dropped by a large percentage. Fans located at the front of the unit are used to draw in air, and we were able to generate air speeds of anywhere from 0.5 meter per second to 1 meter per second. A series of tubing was connected to the heat exchangers in series, and it was attached to either a coolant unit like the one seen here, or a heating unit, where we could push either hot or cold coolant through the heat exchangers. Cold coolant would drive the dehumidification process, while hot coolant would drive the desorption process. And I will now show you our first test run with the dehumidification process. Starting with our outlet sensor, we had a starting relative humidity rating of between 63 and 62 RH. And then our inlet at this point was reading approximately 60 RH. So we started with an inlet RH of about 60% and an outlet RH of about 63%. And our hope is that by running the fans and the coolant through the system, we are able to drop the RH of the air significantly so that the inlet is a higher RH than the outlet.
Should be on.
Is it moving?
It's running down slowly.
Chiller's on, fan's on. So now at your inlet. So at the inlet, we're sitting around 64 RH, 23 C. And on the outlet, we're seeing 55 at around the same temperature. So RH is dropping. It's not affecting temperature much, but the RH is definitely like I said, I'm hovering at about 55 right now. And our inlet's at about 63, 64. As you can see in this time lapse, the gel itself swells as it absorbs water, and we were successfully able to show that we could drop the relative humidity by up to 10% over just 5 gel-coated heat exchangers. We then switched over to a desorption process where we ran hot coolant through the system to heat the gel up to the point where the water would evaporate out of the gel and return to the atmosphere in the form of water vapor. Future innovations on this project can be done to claim that water vapor and collect it as potable water. We took another time lapse during the desorption process. You can see that the swelling of the gel slowly reduces as water leaves the gel and slowly returns to the atmosphere. The end result of using the HYDRA is a higher energy efficiency in the HVAC process and reclamation of potable water.